In our lesson today, we're going to start by talking about tree diagrams. A tree diagram is very useful if you're looking to see what all of the possible outcomes are for a certain event. Okay, a tree diagram will help us create a list, which we call our sample space. So let's take a look at our first example. It says Tina, Jack, and their dog Jones are making sandwiches for their picnic. They want a variety of sandwiches, so they've asked us to construct a tree diagram to help solve probability questions that follow below. If you look at the table, there are three different items that we're going to be using to make our sandwiches. There are breads, there are spreads, and then there are the fillings. For the breads, they have a choice of wheat bread or rye bread. For spreads, they can either have mayonnaise or mustard. And for fillings, they can either have turkey, ham, or cheese. Okay, we're going to say that a sandwich consists of one type of bread, one type of spread, and one filling. And so what we want to do is make a list of all the possible sandwiches that they would be able to make with those ingredients. Okay, so what we're going to do is create a tree diagram. And what we're going to do first is make our choice of breads. Notice in the bread column right here that there are two different kinds of breads, wheat and rye. The way that you make your tree diagram is that you make a number of branches based off of the number of choices you have for each part of the event. Again, our event is making sandwiches. The first thing that we're going to choose is the type of bread. Since there are two breads, notice our tree diagram here starts with two different branches. At the end of the branches, we're going to label what those choices are. We could have wheat bread, or we could have rye bread. Those are your two different choices of breads, wheat or rye. Then, after you choose a bread, the next thing you have to do is choose the kind of spread that you want to put on it, either mayonnaise or mustard. Okay, now, the type of bread that you get doesn't change the type of spread that you can get. So if you chose wheat bread at the beginning, you still have two choices of spreads that you could choose. You could have mayonnaise, or you could have mustard. Okay, so off of wheat, we had two different branches, one for each type of spread. Well, it's the same thing with the rye bread. The type of bread that you choose doesn't influence the spread that you could have. So if you chose rye bread, you still have two different choices of spreads. So we'll make two branches off of rye bread. And your choices, once again, are mayonnaise or mustard. There we are. Okay, so you can see our tree diagram starting to take shape here. We had two choices of breads. Off of each bread, we have two different spreads that we can choose from, mayo or mustard. The last thing that we have to choose is the type of filling that we want. Okay, so there are three types of fillings, turkey, ham, and cheese. The bread and the spread choice doesn't affect the type of filling that you had. So if you had wheat bread and mayo, you have three choices of fillings. You could either have turkey, you could have ham, or you could have cheese. So we put three branches off of mayo. But it's going to be the same thing for the mustard. If you had wheat bread and mustard, you can still choose either turkey, ham, or cheese. So once again, we have three branches, and we're going to label turkey, ham, and cheese off of each of the branches. Okay, well, it's going to be the same thing with the rye bread and the spread that you chose down there. If you did rye bread with mayo, once again, you have three choices of spreads, either fillings rather. You have turkey, ham, or cheese. Same thing as if you chose rye bread with mustard, you have three fillings to choose from: turkey, ham, and cheese. And this is your completed tree diagram. So you choose a bread first, then after you choose the bread, you choose the spread that you want, and then after the spread, you choose the filling that you want. We are now ready to create the list, which again is called the sample space. The list of all possible outcomes is called the sample space. The way that we're going to make our tree diagram, or excuse me, our list, our sample space, is by following the branches on the tree diagram. So here we are at the beginning of our tree diagram. We're going to follow the branches. Our first possible sandwich would be wheat bread with mayo and turkey. So I'm going to put W for wheat, MA for mayo, and T for turkey. There's our first possible sandwich, wheat bread, mayo, and turkey. We could then choose wheat bread, mayo, with ham. Wheat bread, mayo, and ham. Then we could do wheat bread, mayo, and cheese. Wheat, mayo, with cheese. Or we could have wheat, mustard, turkey. Just keep following the branches. I'm going to put MU for mustard and T for turkey. Wheat, mustard with ham. Wheat, mustard with ham. And then wheat, mustard with cheese. Wheat, mustard with cheese. Those are all the possible sandwiches that you could have with wheat bread. Now we have to do the same thing with the rye bread. So once again, we're just going to follow our branches until we make all the different possible sandwiches. So our first one is rye, mayo, turkey. Rye, mayo, turkey. Rye, mayo, ham. And then rye, mayo, cheese. Rye, mayo, cheese. Now rye, mustard, turkey. Rye, mustard, turkey. Rye, mustard with ham. Rye, mustard with cheese. Okay, so there is your list of all of the possible sandwiches. At the bottom of my list, I always like to count them up so that I know how many possible sandwiches there would be. I count them up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different sandwiches we would be able to make with these ingredients. Okay, so this is your tree diagram and the sample space for the ingredients that they listed in this table. Now that we've made our tree and our list, we're ready to answer some questions. They tell us that after Tina and Jack sit down for their picnic, they decide to go for a walk. Jones realizes that they've left their picnic basket unattended. If Jones randomly snags a sandwich out of the basket, what is the probability of getting the following sandwiches? So in question number one, they want to know what's the probability of getting a sandwich that has wheat bread with mayo and turkey. And so to answer that question, what we're going to do is take a look at our list. We're looking for wheat bread, mayo, and turkey. Okay, and so we look at our list. All the wheat breads are right up here at the top with mayo, so that's these top three. But with turkey, there's only one. The very top one right here has wheat, mayo, and turkey. Remember that probability is a fraction. It's the number of items that you want over the total number in your sample space. There was only one sandwich that was wheat, mayo, and turkey out of the possible 12 sandwiches that we could make. So the probability of getting this sandwich is 1 out of 12. Question 2, what's the probability of getting a sandwich that's on rye bread with mustard? So once again, we're going to create a fraction. We know it's out of 12 sandwiches. Now we'll count our list. How many have rye bread and mustard? Rye and mustard. Well, rye are all the ones at the bottom. Rye with mustard, there's 3 of them down here. These bottom 3 are rye with mustard. So our probability would be 3 out of 12. And then you could simplify that down to 1 out of 4. Question 3, what's the probability of getting a sandwich that is on wheat bread? Well, once again, there are 12 possible sandwiches. That's my denominator. Let's count the number of wheat bread sandwiches. Okay, the wheat bread sandwiches were the ones at the top here. There's 1, 2, 3, 4, 5, 6 of them that are on wheat bread. So it's 6 out of 12 for the probability, which we can simplify down to 1/2. Question 4, what's the probability of getting a sandwich with mustard? So let's count now the sandwiches with mustard. Mustard was one of the spreads, which is in the middle. So that's mayo, mustard. There's 1, 2, 3. Mayo again. 1, 2, 3 more mustard. That's a total of 6 sandwiches that have mustard. 6 out of 12, which again can be simplified down to 1/2. And finally, we need a sandwich that has mayo and ham. Mayo and ham. So we're looking for mayo and ham. Notice they didn't say what type of bread. So it could be either wheat bread or rye bread. Mayo and ham, there's one right here that's on wheat bread. Mayo and ham, there's another one down here that's on rye bread. None of the others have that, so that's going to be 2 out of 12, which you could then simplify down to 1 out of 6. In our next example, we're going to be spinning a spinner that's labeled 1, 2, 3, and 4, and then flipping a coin, which we know has two sides, heads and tails. We want to make a tree diagram and then list all of the possible outcomes that would exist when you spin the spinner and then when you flip the coin. Okay, so what we're going to do is start with the spinner. Okay, we're going to start with the spinner. I'm not going to make two branches, one for spinner, one for coin. No, I'm going to look at each one of these individually. I'm starting with the spinner, and notice that there are 4 different sections to that spinner. So that means that there are 4 possible choices, so I need to have 4 different branches for my spinner. And I'm going to label them 1, 2, 3, and 4. Those are the possible outcomes that you can get when you spin the spinner. Now we need to, off of each of the numbers, list the possibilities when you flip the coin. The number that you get on the spinner doesn't change what you can get on the coin. On the coin, you can either get heads or tails. So if you landed on 1 on the spinner, you could get heads or tails on the coin. Same thing with 2 on the spinner. You can get heads or tails on the coin. Same thing with the 3. You can get heads or tails on the coin. Or if you spun a 4 on the spinner, you can still get heads or tails on the coin. So this is what your tree diagram looks like. Now again, let's make that list, which once again is called the sample space. All the possible outcomes, follow the branches. So we're going to follow the branches. We could get 1 on the spinner, heads on the coin, 1 with heads. 1 on the spinner, tails on the coin, 1 with tails. 2 with heads, 2 with tails. Follow the branches. 3 with heads, 3 with tails, 4 with heads, and finally 4 with tails on the coin. Count them all up. I like to put my number 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes when you spin that spinner and when you flip the coin. Now that we have our tree and our list done, let's answer the following probability questions. Number 1, they want the probability of getting an even number on the spinner with heads on the coin. All right, even numbers. The 2 even numbers are 2 and 4. So we're looking for 2 and 4 followed by heads. There's 2 with heads. There's 4 with heads. That's a probability of 2 out of 8. All right, that can simplify down to 1 out of 4. Okay, so out of the 8 possible outcomes, 2 of them were even number followed by heads. 2 out of 8 simplifies to 1 out of 4. The next one is the probability of spinning a 1 or a 2 followed by tails. A 1 or a 2 followed by tails. So we're only looking at the top 4 because those are the only places where you can get 1 or 2 on the spinner. Then it has to be followed by tails. So that would be 1 with tails and 2 with tails. So once again, we've counted 2 possible ways of that happening out of the total 8. So 2/8 is the probability, which simplifies again down to 1/4. Question number 3 asks, what's the probability of getting a number that's bigger than 1? Okay, so again, we know there's 8 possible outcomes. Now let's count how many of them where you get a number that's bigger than 1 on the spinner. So obviously these 2 are out because 1 isn't bigger than 1. But everything else has a number bigger than 1. So 1, 2, 3, 4, 5, 6 out of the 8 have a number bigger than 1. That would simplify down to 3/4. In some questions, you might only want to know how many possible outcomes are there. And if you don't want to make a tree diagram and then list all of them, there's something that you can use which is called the counting principle, also known as the multiplication principle. The counting or multiplication principle is a very important principle in probability. It tells you how many items are in the sample space. This can be used for more than one event. All right, could be a game that's played twice. It could be for 2 different events, or it could be for more than 2 different events. All right. When you do the multiplication or the counting principle, the answer that you get is a number that is used as the denominator of the probability ratio because it will tell you how many possibilities there are. Okay, so for example, in number 1, The event is throwing 2 dice. Die 1 has 6 possible outcomes. Die number 2 also has 6 possible outcomes. How many items are in the sample space? That's what we're trying to figure out. So instead of making a tree and then listing out all of the possibilities, we're going to figure out by using the counting principle, also known as the multiplication principle. So what we need to do for die number 1 and die number 2 is list how many outcomes there are for each. Die 1 has 6 possible outcomes, and die 2 also has 6 possible outcomes. To get the total number of outcomes, well, this is called the counting or multiplication principle. You multiply these numbers together. 6 times 6 means that there are 36 outcomes possible when you roll 2 dice. Okay? So the way that the counting principle works, you take the number of choices and you multiply again by the number of choices for the next event, and that equals the number of outcomes. Choices times choices is equal to outcomes. In our second example, we're going to be spinning a spinner that's labeled A, B, C, D, and then we're going to be flipping a coin that has heads and tails. We don't want to know what all of the possible outcomes are. We just want to know how many there are. So again, we said right here in the box, you take the number of choices for each event and you multiply them to get the number of outcomes. So on our spinner, we have 4 different choices, A, B, C, and D. On the coin, we have heads and tails, so 2 possible choices. And you multiply them together to get the total number of outcomes. 4 times 2 is equal to 8. There are 8 outcomes when you spin a spinner with 4 sections and when you flip a coin. And in fact, we knew that up above because that's what we did in this last example here. We had a spinner with 4 different sections, a coin with 2 different sides. 4 times 2 is 8. And we listed them out, and there were indeed 8 possible outcomes. All right, so this is proof that the counting principle works. In our next example, it says that the Trail Steakhouse has 2 kinds of salad, 5 kinds of steak, 4 types of dessert. The first question wants to know how many different dinners could you order there if a dinner includes a salad, a steak, and a dessert? Okay, so you have to make a choice of 3 different items: a salad, a steak, and a dessert. Okay, we want to know how many possible meals exist based off of the number of choices that they've given you. So for salads, you have 2 salads to choose between. For steaks, you have 5 different steaks to choose between. And for desserts, there are 4 of them. In order to get the total number of outcomes, you have to take your number of choices for each part and multiply them together. 2 times 5 is 10. 10 times 4 is 40 different dinners. Okay, based off of 2 salads, 5 steaks, and 4 desserts, you could make 40 different dinners. In part B, they want to know how many different meals could you order if they add 2 more salads, 1 more steak, and 1 dessert to the menu. Okay, so again, we have a choice of salad, a choice of steak, and a dessert choice. Now, they're using the same amount that they had before, but they're going to add in more for each item. So before, they told us that they had 2 different salads. If they add in 2 more salads, that's 4 different salads you could choose from. All right, earlier they said that they have 5 steaks. They're going to add in 1 more, which is a total of 6 steaks. And before they said that there were 4 desserts. They're adding in 1 more to the menu, which means that there are 5 total desserts. To get the total different number of meals this time, you would have to multiply 4 by 6 by 5. Okay, 4 times 6 is 24. 24 times 5 is equal to 120. So there would be 120 different dinners that you would be able to order if they add in just 2 more salads, 1 more steak, and 1 more dessert. In example 3, they tell us that Lenny is a pilot. He has 2 cars that he can drive to the airport, and when he gets there, he has a choice of 6 airplanes to fly to another town for a meeting. When he arrives, any one of 3 taxi cabs can pick him up to take him into town. So question A wants to know how many different combinations of transportation are possible for his trip. So we have to make a decision out of 3 different items. He has to choose a car. Then when he's at the airport, he has to choose a plane. And once he gets to the new town, he has to choose a taxi in order to get to his meeting. Okay, so we're going to list how many choices there are for each. They tell us that he has 2 cars. When he gets to the airport, there are 6 planes to choose from. And when he gets into town, any one of 3 taxis can take him to where he needs to go. So all we need to do now is multiply the number of choices that we have. 2 times 6 is 12. 12 times 3 is 36 combinations. Lenny has 36 combinations of transportation for this trip. Now, part B, it says that when Lenny returns, he can still catch any one of the 3 taxis. However, he has to fly back in the plane that he brought, and then he has to drive home in the car that he brought to the airport. So how many combinations are possible for his trip home? So once again, there's going to be a car involved, a plane involved, and a taxi involved. And for the car, it says that he has to drive home in the car that he brought to the airport. So there's only one choice there, only one car that he drove to the airport. He also has to fly back in the plane that he took to the other town. All right, so only one plane he flew in. But when he returns, he can still catch any one of the 3 cabs to get him back to the airport. So once again, we're going to multiply the number of possibilities this time. 1 times 1 times 3. There are only 3 combinations for Lenny on his return trip home. In the next set of problems, we're going to look at number problems like phone numbers, combinations, and zip codes. All right, these types of problems involve the digits. The digits that we use to make up our numbers in everyday life are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, those are the digits that we use, and if we count them up, you would count that there are 10 different digits that we use to make up the numbers we use every day. In question number 4, it says we're going to be choosing the last 3 numbers in a 5-digit zip code. If the first digit is 5, the second digit is 2, and no digit is used more than once. What we're going to do on the lines, it's a 5-digit zip code, so I've got 5 different lines here. You're going to list the number of choices on the lines. You are not going to put the actual numbers there. Here's what I mean by that, okay? What we're doing, it says that the first digit has to be the number 5. I'm not putting a 5 there, okay? I'm putting how many choices they've given me for that digit. Since it has to be the number 5, they've only given me 1 choice for that digit, okay? For the second digit, they told me right here that the second digit has to be the number 2, all right? Once again, I'm not putting a 2 right here. I'm putting how many choices they gave me. Since it has to be the number 2, once again, that's only 1 choice that they've given me, okay? Now, for the other 3 digits, there are no qualifications except I can't use any digit that I've already previously used, okay? So in the first spot, I used the digit 5, so I would say, well, that's gone. And in the second spot, I already used the digit 2, so I would say that that's gone. For the third digit, I can use any digit that's remaining, so I have to count how many choices I have left. Well, if I started with 10 and I took out 2 of them, that means I have 8 choices for the third digit, okay? Now, of these 8 choices, I'm only going to use 1 of them. The one that I choose, I can't use again. So for the fourth digit, I can use any of them that I had before except for the one that I used here, which means I'm going to have only 7 choices for the fourth digit. Okay, whatever digit I used here, I can't reuse it. So instead of having 8 choices, I have 7 choices. And now for the last digit, again, I had 7 choices before. I'm going to pick one of them to use that I can't use again. So that means I'm going to have 6 choices for the last digit. Okay, so all you need to do to figure out how many zip codes exist is multiply the number of choices for each spot. 1 times 1 times 8 times 7 times 6. If you punch that into your calculator, you would end up with 336 zip codes that are possible. Okay, so again, on these lines, you're putting how many choices you have. You're not making the actual zip code. In example number 5, once again, we're going to be creating a 5-number zip code. So we've got our 5 spaces listed out here. We're going to be choosing the last 3 digits in that zip code. The first digit is even. The second digit is a different even digit. And once again, no digit can be used more than once. So we're going to put how many choices we have for each digit in our zip code. They said the first digit had to be even. If you look at your list of digits up above, the even digits are 0, 2, 4, 6, and 8. That's a total of 5 choices that you have for the first digit. Now, of these 5 digits, I'm only going to use one of them, but I can't use it again. So for the second digit, where it's a different even digit, instead of having 5 choices, I'm now going to have 4 choices. Okay? Now, for the last 3 spots, there are no qualifications that they've given me, except I can't use any digit that I've already used. Okay, so remember, there are 10 different digits. In the first spot, I had 5 choices, but I used 1 digit. In the second spot, I had 4 choices, but again, I used 1 digit. So that's a total of 2 digits that I've used already that I can't use again, which means that I have 8 choices for my third digit. Of the 8 choices, I'm going to use one of them, meaning that I can't use it again. So for the fourth digit, I'm going to have 7 choices. And then for the last digit, I'm going to have 6 choices because, again, the digit that I used in this spot, I can't reuse again. So instead of having 7 choices again, I'd be left with 6 choices at the end. Now I'm going to multiply these 5 numbers together to get my total number of zip codes. So when we do 5 times 4 times 8 times 7 times 6, that's going to give us an answer of 6,720 zip codes that are possible. In example 6, they want to know how many 5-number zip codes can be created if the first number cannot be 0, and each of the numbers may be the same. So I can repeat numbers in this example. Okay, so we've got our 5 spaces listed out for the 5 digits in the zip code. They've told me that the first number can't be 0. So if I ignore 0, I still can choose any one of those 9 numbers. So I have 9 choices for the first digit. Now, for all of the other ones, there are no qualifications given. I can bring 0 back into the mix, and I can reuse the number that I used the first time. So all of the digits are in play for the second digit. I have 10 choices that I can make for the second digit. Again, I'm only going to use one of the numbers here, but I can reuse it, which means that I have 10 choices for the third digit. The number that I use here, I can reuse again, so I have 10 choices for the fourth digit. And the number that I use here, I have 10 choices for the fifth digit because I can repeat that fourth number as well. So these are the number of choices I have for each digit in my zip code. To get the total number of zip codes that I could create, I'm going to do 9 times 10 times 10 times 10 times 10. And when you do that, that's going to give you 90,000 zip codes that are possible. So when you start to be able to reuse numbers, the number of zip codes increases dramatically.